All right, rational expressions. Rational expressions are just algebraic fractions. So they're fractions, but they have letters in them. So just like with regular fractions, you have a numerator and a denominator. Numerator's on top, denominator's on the bottom. Rational expressions are going to have letters and numbers. They're going to be algebraic. And in this example, we have x in the denominator. Well, what do we know about fractions in the denominator? There's certain values that cannot be in the denominator of a fraction. So in this case, we have a restricted value of x, a value that x cannot be. And in this example, x cannot be equal to 0. Because if x was equal to 0, I would have 3 over 0. And 3 divided by 0 is undefined. So you can never have a 0 in the denominator. Your numerator can be 0, but your denominator cannot be 0. So if I had something like 5 over x minus 3, there's two ways they could propose this question. They could say, state the restricted values. Or they could ask you to state the domain. The domain is all the values x can be. Restricted values are what x can't be. So in this example, if I was to ask you, what can't x be? What are the restricted values, right? Well, then you're thinking to yourself, well, what's going to make the denominator 0, right? What value will make the denominator 0? And I have 5 over x minus 3. So you're saying what value will make this denominator equal to 0? So you could actually create an equation You might not need to in a problem this simple, but you could create an equation for what value of x will this denominator be equal to 0? And then you could do, plus 3, x is equal to 3. When x is equal to 3, the denominator will be equal to 0. Therefore, x cannot be equal to 3. And that's how we would state a restriction. If they ask you to state a domain, well, even if you're stating a domain, I think it's a good idea to first state the restriction so you have it clear in your head what x cannot be. Because now you could say, well, x can be x is equal to all real numbers except x can't be equal to 3. That's one way of writing it. Another way is to use interval notation. You could say your domain is from negative infinity up to 3, not including 3, and then from 3 to positive infinity. That's a way to write it in interval notation. It's from negative infinity to 3, not including 3, and then it's from 3, not including 3 again, to positive infinity. If you were asked for the domain, that's what they would be looking for. So here are some examples that you could try. It asks you to state the restricted values of x. So let's just remember, in order to state the restricted values of x, all you have to do is set the denominator equal to 0 and then solve. And then state the restriction. One, two, three. So why don't we try those? So if we were to follow the procedure I set, we would set the denominator equal to 0, and then we would solve for x. So in this case, we would add 7 to both sides of the equation, so x is equal to 7, which means if x was equal to 7, the denominator would be equal to 0. We can't have 0 in the denominator, therefore x cannot be equal to 7, because it will create a 0 in the denominator. You have to do all that work? No. You could just look at this and say, what's going to make the denominator 0? What minus 7 will give me 0? 7 minus 7 will give me 0. Same thing here. You don't have to do all the math. We could just look at the denominator. And right here, I know right away that x cannot be equal to -4, because -4 plus 4 will give me 0. We're only concerned with the denominator because I could have a 0 in the numerator. I could have 0 over 6. That's equal to 0. It's when I have 0 in the denominator, we get an undefined value. So that's why we're only focusing on the denominator. In this next example, I would set the equation equal to 0, plus 7 plus 7. 2x is equal to 7. Divide by 2, divide by 2. So x is equal to 7 halves. So my answer is x cannot equal 7 halves. There's a trick here also, so I don't have to do all this math. The answer will always be this value on top of this value, opposite sign. 7 over 2 positive. 7 over 1 positive. 4 over 1 negative. 5 over 3 negative. So is this value on top of this value, opposite sign. Right? 5 over 3 negative. That's what we got. So if we continue on here, 4x is equal to 0. Divide both sides by 4. So x is equal to 0. Therefore, x cannot be equal to 0 because it will create a 0 in my denominator, which makes sense. 4 times 0 is 0. It checks. Here we have two binomials. So really, we're going to have two equations here. We're going to have x plus 3 is equal to 0, and x minus 6 is equal to 0. Because if 1 is equal to 0, 0 times anything is 0. So only one of them has to be equal to 0. Minus 3, x is equal to negative 3, plus 6, x is equal to plus 6. So those are my restrictions. X cannot be negative 3, and x cannot be positive 6. In this example, we have a quadratic. We have an x squared in this case. Well, in order to do this, we want it to look like this. We want it in factored form. So instead of having 4x plus 1 over x squared minus 5, I'm going to write 4x plus 1 over x plus 5, x minus 5. So now the problem looks just like the prior problem. So I'll follow those same steps. I'm going to write two different equations. X plus 5 is equal to 0, and x minus 5 is equal to 0. Therefore, x cannot be negative 5, and x cannot be positive 5. So we have two restrictions. In this next example, we want to do the same thing. It's written in quadratic form, y squared plus 5y plus 4. So I want to see it in factored form. So my numerator will stay the same. My denominator, if I factor it, y times y is y squared. 4 times 1 is 4, and my signs are the same. Once I have it factored, I want to set each factor equal to 0. Y plus 4 is equal to 0, and y plus 1 is equal to 0. So I know y cannot equal negative 4, and y cannot equal negative 1. Those will be my two restricted values. So we're going to continue by simplifying rational expressions. Simplifying rational expressions, simplifying means we're going to be reducing. And rational expressions, like I said before, are really just algebraic fractions. Right? We all know how to reduce fractions. Right? In this example, you can recall 4/10. If I were going to reduce 4/10, we all agree that this would be 2/5 in reduced form. And it's 2/5 because we know that 2 goes into both the numerator and the denominator. So really, we're factoring out a 2 from the numerator and the denominator. So we know that 2 times 2 is 4, and 5 times 2 is 10. Right? We're saying 2 goes into both the numerator and the denominator, and if I take away this 2, I'd be left with 2/5. That's what's really going on. You know, you do it intuitively because you're used to it. So, but that's really what's going on in your head. You know that there's a 2 that goes into both of those. So you're factoring it in your head. You know 2 is a factor of the numerator and 2 is a factor of the denominator. And then you're taking out that factor. So what did you do? Let's do that procedure again. We factored the numerator and denominator. And then we canceled out the like factors. The factors that are the same. So if we're able to reduce 4/10, we should be able to reduce x squared minus 25 over x squared plus 10x plus 25. I'll give you a second. Think about it. Well, if we follow these procedures, factor the numerator, factor the denominator. Well, if I'm factoring my numerator, this is the difference of two perfect squares. This could be factored as x plus 5, x minus 5, all over the factors of my denominator, which looks like it's going to be a perfect square trinomial. X times x gives me x squared. 5 times 5 gives me 25. And my inners and outers give me 10. So we factor the numerator, we factor the denominator, and now we cancel out the like factors. So I'm going to have x minus 5 over x plus 5. In this example, like I said, in the textbook, they might say set restrictions. If it says set restrictions, we set restrictions before we cancel. This is where we would set restricted values. Before we cancel. In this example, it wouldn't make a difference because my restrictions here would be x can't be negative 5 and x can't be negative 5. That would be my restricted value. And it wouldn't make a difference in this example because it's the same after I cancel as it was before I canceled. In this example, we want to factor and cancel. So up top, the first thing I do when I factor, my first step for factoring is always look for a GCF. Looks like I could take a 4 out. That would leave me with x minus 2. On the bottom, there's no GCF. This is a trinomial with a leading coefficient of 1. So I know x times x gives me x squared. 2 times 2 gives me 4. My signs are going to be the same, and they're both negative. So in this case, I would set my restrictions. X cannot be equal to positive 2, and x cannot be equal to positive 2. That would be my restriction. I don't have to write it twice. And then I could cancel out my like factors, and my final answer for a simplified rational expression would look like that. Let's look at this third example. And let's assume that the question asks for you to simplify the rational expression and state restrictions. So I'm going to factor my numerator. Looks like I'm going to have 4 times 4 will give me 16 minus minus. My denominator, I could factor out a GCF of 3, x minus 4. And at this point is where I would set my restricted value for x. So in this case, I know that x cannot be equal to positive 4. It's my restricted value. I cancel out my like factors, and my final answer for my simplified rational expression is x minus 4 over 3. In this case, we could see that it makes a difference that we set our restrictions before we cancel, because if we set it after we cancel, there would be no restrictions. And after the fact, there are no x's. So you set your restrictions before you cancel. So let's look at multiplication and division of rational expressions. Hopefully you guys can remember how to multiply and divide regular fractions. Right? If I had 9/14 divided by 3/8, this is a division problem. We know we can't divide with fractions. We're going to have to rewrite this as a multiplication problem. It's the multiplication of the reciprocal, or you might know keep, change, flip. But really, we change to multiplication, and then we flip the divisor. We multiply by the reciprocal. And then we could multiply straight across when we multiply with fractions. But we're going to get some big numbers with 9 times 28 and even 14 times 3. So it's a good idea to simplify at this point. We reduce here. Right? So I know that 14 and 28, well, I know 14, 1 times 14 is 14, and 2 times 14 is 28. I know 14 goes into both of these. Right? 14 goes into this one time, and 14 goes into 28 2 times. The same thing here. I have a 3 and I have a 9. I know 3 goes into 3 once, and 3 goes into 9 3 times. So I rewrote it as a multiplication problem. Rewrite as multiplication. And then I reduce before I do any more multiplication, right? I find the like factors. And then once I find my like factors that I cancel out, I could then multiply straight across. 3 times 2 is 6, and 1 times 1 is 1. So when we multiply across, we get a final answer of 6 for this example. So this problem looks challenging. I have x squared plus 5x plus 6 over x squared plus x minus 6 divided by x squared minus x minus 6 all over x squared minus 9. So if we're going to follow these same 3 procedures, right, we should be able to do this division problem of rational expressions. So the first thing we want to do is we want to rewrite this as a multiplication problem, which really just means rewrite the whole thing over again. X squared plus 5x plus 6 over x squared plus x minus 6 times, and then we have to take the reciprocal, so we're flipping this one, x squared minus 9 over x squared minus x minus 6. Once we rewrite it as a multiplication problem, we want to find the like factors to cancel out. So we want to factor all the numerators and denominators. So if we factor it, hopefully we get this. Once we factor all the numerators and denominators, and now we could start canceling. Now when you cancel, you could cancel only from top to bottom. Not side to side. So you could go vertically or even diagonally, but it always has to be top to bottom. So for example, I can do x plus 2 here and x plus 2 down here. I could do x plus 3 here and x plus 3 here. I could cancel x minus 3 here and x minus 3 here. Once I cancel all my like factors, I multiply straight across. So I have x plus 3, everything cancels out, so this is like 1. X plus 3 times 1 is just x plus 3. And on the bottom, I'm just left with x minus 2. So my final answer is x plus 3 over x minus 2. So to sum things up, I wrote a procedure here, right? Our procedure is we want to, when multiplying, we want to factor all the numerators and denominators. Then we're going to cancel out all of our like fractions, top to bottom. We could go vertically in the same fraction, or we could go diagonally to the fraction next door. Then we would multiply across and leave our answer as a single fraction, right? So let's try these two examples. One's a multiplication problem and one is a division problem. So we could see in this first example, all we have to do is factor out the GCFs. It doesn't look like we could factor anything more than that. And then we could start canceling 2x plus 3 and 2x plus 3 are x minus 5 and x minus 5. And 3 over 3 could cancel out, right? And remember, every time we cancel out, canceling out is not really a mathematical operation. Really what we're doing is we're saying 3 divided by 3 is 1. 2x plus 3 divided by 2x plus 3 is 1. X minus 5 divided by x minus 5 is 1. Right? So this is really just coming out to 1 over, the only thing left on my denominator is 2. So in this case, it looks like my final answer is 1 over 2. 1/2. And I'll scoot this down so we could look at this division problem. Remember, it's division. You can't divide with fractions, so you're going to have to change this into a multiplication problem. Keep, change, flip, or better saying, we're going to multiply by the reciprocal. And the GCF over here, x plus 1, the difference of two perfect squares down here, x plus 2, x minus 2. So I factor all the numerators and denominators. I could cancel out from top to bottom. X plus 1, x plus 1, x plus 2, x plus 2. And that looks like it. It looks like my final answer is x over x, rather x times 3, all over x minus 2, x minus 1.